Good morning. Good morning. Good morning. Good morning. Welcome to another Sunday Morning Papers, the series where I force all of you to share the pain that I'm going through for my research. I hope you are doing quite well today. We are going to have an exciting break in an hour and 20 minutes. So if we're still streaming, there's going to be I gotta go do something. But yeah. In the meantime, okie dokie, where was I? What was it? Okay. I hope everyone is doing quite well today. Yes. There we are. Okay. I got stuff set up. Okay. We're doing well. All right, I'll work on that later. So, today we are going to go through. Oh, I need to set that up. I am like doing well today. Man. Okay. Let's see. I gotta set up my hello. Okay, thank you. I just have to set up my Twitch shenanigans here. Right. So that I can properly monitor the stream in case someone comes in and decides to throw some spam into the chat. We can properly ban them as one should. There we go. There's that. Good. Beautiful. And now we open a private window. And now we go back to enter Twitchy. And then we log in. And then we go, oh, we are Baron. Use SMS instead. Request code. Okay. Two-factor. That is not. Genius. Amazing. Dashboard. Stream manager. Got it. And we're alive. We have all of the bits and pieces put together that need to be put together. So sorry about that. Sorry that took a while, but all right. I think we're ready to rock and or potentially roll. So today, for your enjoyment or pain, kind of depending on how you approach it, we're looking at this. Performance metrics for climate models. All right, this is kind of a follow-up to the last paper we did that we're looking at the Taylor diagrams. And so this is, we might do a little bit of bouncing through this from time to time because again, we're searching for the key pieces that we need, right? So there might be a little of, we don't care about this, we don't care about that. We're just trying to find the kind of the mathematical constructs that are used in this paper, which again is a follow-on, kind of a follow-on. It leans in on that last paper, the Taylor paper that we went through last time. So, but I kind of needed to go through this myself. And so I was like, what better time than on Sunday Morning Papers when I can bring all of you through this as well. I can share the pain. It's fun. Anyway, okay. So let us begin. Climate models are routinely subjected to a variety of tests to assess their capabilities, right? That's ultimately what we're trying to do. We have a bunch of different models, and we're trying to A, select a model, and B, see how good it is. And then we're going to later compare that against some simulation models and see if those are better or worse. Anyway, a broad spectrum of diagnostic techniques are relied on in evaluations of this kind, but relatively little effort has been devoted to defining a standard set of measures designed specifically to provide an objective overview or summary of model performance. That'd be great, because then we could just reference this and say, like, look, here's this is the method that was used here, and we like it. Okay. In this study, we explore issues important to the development of climate models, climate performance, quote, metrics, addressing how such measures can be defined, and by means of example illustrating their potential uses and limitations. We evaluate recent suite of coupled ocean atmosphere general circulation models. So again, these are, this is terrestrial weather stuff, not space weather, but they're looking at complex systems where you have the interplay between the ocean and the atmosphere, right? They're each affecting each other, and so you end up with these feedback loops and that kind of stuff. And so a lot of the models are coupled, right? Ocean atmospheric circulation models, focusing primarily on global scales of the simulated mean annual cycle. Okay, so that's what most of these models that they're looking at. Years ago, standard measures of forecast skill were adopted by numerical weather prediction community. Relying on these metrics, the Working Group on Numerical Experimentation, WGNE, routinely reviews the skill of weather forecasts made by the major weather prediction centers. All right, so they're kind of like the overarching entity that's looking at and comparing these and seeing how they do. The WGNE reports to the World Meteorological Organization Commission for Atmospheric Science and World Climate Research, Joint Scientific Committee, monitoring the NWP performance. In this way, it has provided quantitative evidence of increase in forecast skill accuracy over time, as well as characterizing the relative skill of individual forecast systems. So in general, things have gotten better with the forecasting. Okay. Although the value of climate model metrics has been recognized for some time, there are reasons why climate modelers have yet to follow the lead of the NWP community. First, a set of observables, for example, surface pressure anomalies, have proven to be reliable proxies for assessing overall NWP forecast skill, whereas for climate models, examination of a small set of variables may not be sufficient. So in other words, for these other models, right, that are looking at relatively small regions, right, they're trying to predict the weather in a specific region. Hey, how's it going? Right, so they're trying to predict weather in a specific region. They can go back and look at, they can kind of lean in on, not too bad, just trying to run through this paper. So if you have any interest in the assessment of prediction models, welcome on in. With the smaller scale models, right, it's pretty easy to go and make a couple of measurements, compare it to what the model says, and say, okay, cool, this is good or this is bad. For a climate model, which is large, global and long term, you can't really assess it so easily, right? And so he's trying to talk about. Just for your background, we are looking at the method of assessing models because it is similar to some of the work I'm doing. The specific climate models that they're looking at, we don't really care about so much, so we might jump around through that stuff. But we're looking at the methodology that this paper is trying to put together for taking models that are supposed to predict what's going on and assessing how good they are, right? Ultimately, that's what we want to know. Because climate models are utilized for such a broad range of research purposes, is likely more a comprehensive evaluation will be required to characterize a host of variables and phenomena on diurnal, intra-seasonal, annular, and longer timescales. Due to a succinct set of measures that assesses the importance climate has not been identified. In other words, these large-scale models that are looking at multiple years or multiple seasons within a year, right? They don't really have a defined way of evaluating their effectiveness. Another reason for this lack of accepted standard measure for climate model performance is that opportunities to test the ability to make predictions is limited. NWP, go down, and we go across over here, and over to here, over to here. Yeah, almost there. There we go. Beautiful, perfect. Okay, NWP systems are routinely verified against continuously varying weather conditions, whereas climate models are repeatedly tested against observed climatology that is only slowly evolving, right? If your prediction is on the order of decades, then it takes decades to get a measurement to determine how good you were about this evaluation. And on top of that, you might need multiple measurements to actually be able to make a valid assessment. You do need multiple measurements to be able to make a valid assessment of how effective you're. Hello, Potato. We have a dog. Hello, Potato. How are you doing? Did you get mud in your collar again? Oh, you sure did. Is it getting everywhere? It sure is. Good boy, Potato. Dog has one of those big collars on because he had surgery, and so he keeps going into the mud outside and like digging the mud into the collar, like the space where the Velcro is, where you have two layers, and then bringing that all over the house. Oh, look, there's mud everywhere. Oh, genius. Good job, Potato. I knew we could count on this dog to provide a little comic relief. All right, he's ran off somewhere. That's good. Yeah. What's science without dogs? Okay, anyway. Right. So there are additional factors to consider in developing climate model metrics. A wide variety of variables are of interest, and observational uncertainties are often substantial but poorly estimated. This is important. So for exactly. He's got to insert himself into these streams to make sure that everyone understands that he is part of this as well. Right. So this is an important piece, and this does transfer over, right? There are, I wonder what this looks like. Okay. Observational uncertainties. In other words, the measurements that you're making are going to have errors in it, but the estimate of what those errors look like is pretty poor, right? So it's very difficult to get a solid estimate of how wide your error range is, but there are a whole variety of different variables, and they all have observational uncertainties to them. This is also true with the data that I'm looking at. Some aspects of the climate model simulations are deterministic, while others are not, making a quantitative verification more complex. Right? So some are statistical, and some are Potato. Some are statistical, and some are deterministic. Potato, what are you doing? Yes, you. I hear you. Are you messing with papers to get my attention? Potato, do I need to kick you out of the room? Potato, what are we doing? I hear him. I just hear him pulling down papers and messing around with them. You will give me one quick moment. Potato. Oots. Potato. I see you are very excited. I know you're such a good boy. And you're a very excited good boy. Can you be a very good, excited good boy elsewhere? I love you. I love you very much. Hey, no, come on, buddy. Oh, 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 oh. Thank you. He did not want to leave the room. I only have an ad starting soon. He did not want to leave the room, but I had to kick him out. How unfortunate. There are now papers strewn all over the back of my room because he pulled them all down and was like, if I paw at these, I'll get your attention. Yay. Anyway. Wait for it. Is he going to whine at the door? He hasn't whined at the door yet. That is precisely, absolutely what this dog is doing. He's like, if I mess around with all the papers, maybe he'll love me more. By which I mean, pay attention to me more. This poor dog is so unloved. Let me tell you, so unloved. Okay. So I'm just gonna give it because we have an ad going for a minute, and so in the interest of not leaving the poor people who are stuck in ads out of our continuation of the paper, I'm just gonna chat for a little bit. So for the background for some, we are looking at space weather stuff, right? Which is ionosphere. So there's a lot of, it's a coupled system with the neutral atmosphere. There's a lot of influence back and forth. So in the same way that the neutral atmosphere is also coupled with the ocean, right? So I was talking about the ocean atmosphere coupled systems. So we have a lot of very similar processes going on to what they're talking about here. So yeah, 4, 3, 2, 1. Welcome back. All right. Cool. So I was just saying that the stuff I'm working on is space weather, so ionospheric stuff that's interconnected with this neutral atmosphere. Anyway, but let's keep on rolling. In the face of these challenges, initial work in the area has nevertheless been carried out. The WGNE has encouraged development of standard diagnostics. Lanel's got them, and has established benchmark experiments through model intercomparison projects. So the guy who did Taylor, who did the other paper that we did last time, actually worked at Lanel. So I bet I think that's what he's referencing with this. Many of the metrics described in this article have been routinely calculated by Program for Climate Model Diagnosis and Intercomparison Committee and have been presented in public forums attended by climate modelers. Until now, publication of these results have been withheld because of the real danger that unwarranted importance might be attributed to these measures of model performance, right? Without appreciation of their limitations. As with any such things, right? You're trying to see how these models function, and the metrics that you're going to use are necessarily restricted, right? You're not going to be perfectly capturing what's going on, and if you don't understand both the positives and the negatives of the metrics that you're using, you'll be in trouble. As a completely side note, there is a corollary to this, in my opinion, which is that metrics drive behavior. And so if you're at work somewhere, right, and you have a metric that is evaluating how well you work in some way, your effort is going to maximize that metric. right? So if I want to understand, like, imagine a company is trying to figure out how effective the workers are doing X, Y, Z, right? They're going to figure out some way of counting something. And what that is going to do is ensure that your workers maximize that. Right? And if that metric is, say, coincidental to the well-being of the organization, sometimes the well-being of the organization can be undermined by that metric. And so this is, to go off on a little bit of a tangent, in my humble opinion, the problem with using shareholder value as a metric of effectiveness of a company, right? Because the company is going to maximize shareholder value, and then they're going to be absolutely willing to literally bury the long-term well-being of the company if it increases shareholder value now, right? Because that's the metric of success. So metrics drive behavior, and as soon as you use a metric to test behavior, that metric is no longer useful as soon as people know that they're being evaluated by that metric. Anyway, sorry. That was a random tangent. Oop, that was entirely unnecessary, but is something important to note, in my opinion. Just in general about how people function. Okay. Anyway, for the purposes of this study, the term metric will be restricted to scalar measures. Many popular statistical measures are consequent with this definition. For example, mean error, root mean squared error, correlation, and variance, right? These are all statistical terms that tell you how close things are. We also limit ourselves to metrics that directly compare model simulations with observationally based reference data, right? So, and distinguish them from diagnostics, which are more varied and include maps, time series distributions, etc., right? So in this case, he's just looking at things where you're making a prediction about what's going to happen in at time frame X in location Y, and then you go to time frame X, or you go to location Y at time X and you make a measure, and you now have a way to directly compare the estimate that what you said is going to happen with what actually happened, right? And then you want to know, well, how effective was I at measuring it? And if you're just measuring a single thing, like say my model is predicting temperature at this location at this time, right? That's easy. I can go to the location at that time, measure temperature, and say, cool. But what if my model is putting out 15 different predictions, right? It's saying temperature and, I don't know, rainfall and atmospheric pressure and, I don't know, pick whatever you want, right? And say it does better at some of them and at other ones. And let's say you have two different models that you're trying to compare versus each other to figure out which one's the best. And they're both making predictions on all of these different variables. And some are better and some are worse. And how do you go through and evaluate, well, which is overall a better model that gets me closer to what I want to get to, right? That's part of the big question with this. Right. Consistent with this nomenclature, metrics can be derived from diagnostics, generally resulting in condensation of the original information. In this regard, we expect metrics to provide symptoms of problems, but to be less informative than diagnostics for illuminating their cause, right? So typically a metric is going to tell you that there is something wrong, but not necessarily why that something is wrong. All right, in section 2, we describe both the observationally based reference data and the model simulations used in the study. In section 3, we introduce, okay, let's just tell them what you're going to do, what you're going to tell them, then you tell them what you told them, usual. Okay. Section 2, model and reference data sets. The CMIP3 simulations. The models evaluated in this study come from nearly all major climate modeling groups and are listed in Nope. Dang it. Hard to do this with a pen. Okay, cool. We're at the right spot. And we just go up. I'm doing this on like a drawing tablet, so moving things around with the pen is interesting. Okay, table 1, recently part of CMIP 3, these groups performed an unprecedented suite of coordinated climate simulations. This ambitious undertaking was organized by the WCURPS Working Group on Coupled Modeling. The WCUCM designed this set of experiments to facilitate the science of model evaluation they felt needed to be addressed in the 4th assessment report. Okay. We don't care about the why. A bunch of people did this stuff, right? Our analysis focused on 20th century simulations, which were forced by a variety of externally imposed changes, such as increasing greenhouse gases and sulfate aerosol concentrations, changes in solar radiation, and forcing by explosive volcanism. These are all things that affect weather, right? The what's in the atmosphere, from human-made emissions to volcano emitted stuff, and how strong the solar radiation is, blah 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 blah. Okay. Since considerable uncertainty as to the true forcing remains, the forcing is not the same for all models. Rather, these runs represent each of the group's best efforts to simulate 20th century climate. Models were, quote, spun up under conditions representative of the pre-industrial climate, nominally 1850. From this point, external time-varying forcing consistent with the historical period was introduced with the simulations were extended through the end of the 20th century. In other words, because what they're evaluating is the models themselves, they went and looked at past data, right? They went and predicted things. They said, all right, I have my model set up, and I'm going to predict what it's going to be in the 20th century when we already have data through the 20th century, so we can say how effective the models were. Although the CMIP3 archive includes daily measures for a few fields, and even some of the data sampled every 3 hourly intervals, we shall focus here solely on the monthly mean model output, which are fine. This provides reasonably cohesive model performance. They're looking over the course of a century. They're gonna the granularity they're looking is down at a month's scale. Okay. But excludes evaluation some aspect of climate, such as frequency intensity of extratropical cyclones and the frequency of some types of extreme events that would only be evident in the daily or 3 hour data, right? So whatever, sure. More of our climatologically important quadratic quantities such as heat and momentum fluxes are not available in the archive and will not be considered here. The initial list of fields evaluated here should be in future studies expanded to include other important aspects of climate. Right. So in other words, when he's evaluating, he's not looking at all these models spit out huge amounts of data, right? And they're estimating a whole slew of different types of results. So they're focusing on a certain subset. In this study, we focused mostly on climatology of the last 20 years of the 20th century, 1980 to 1999. During this period, the observational record is the most reliable and complete, largely due to the expansion and advances of space-based remote sensing. Turns out if you have a satellite looking down, you can get a whole lot of information about the atmosphere. Reference data. The climate characteristics of particular interest to us in this study range from large to global scales, so we restrict ourselves to observationally based data provided on global grids that are readily comparable to climate models. One limitation of most reference data sets is that it is in general difficult to estimate their observational errors. In other words, no matter what you do, when you make a measurement, you have an error in your measurement. You have a certain amount of unknown in your measurement. Now, you can try and reduce that by Having equipment that is is designed and functions down to a certain scale. It'll have a very relatively small error scale. You can try and use multiple pieces of equipment that are measuring the same thing, so you can sort of narrow down some of your error, your error bars, things like that. But regardless, no matter what you do, there's always gonna be some error, and lots of times you don't actually know what the error range is, right? Especially if you're looking at historical data, you don't necessarily know how good the equipment is that was used to generate the data, right? Especially early on. So, oops. There we go. Sources of uncertainty include random and bias errors in the measurements themselves. So, a random error is exactly that, right? You have random fluctuations in your measuring apparatus and in the environment. And you also have bias errors, right? So every time your thermometer is 2 degrees hot, so every time it makes a measurement, it's off by 2 degrees because your thermometer always reads 2 degrees too hot, right? That'd be a bias measurement. Sampling errors and analysis error when the observational data are processed through models or otherwise altered. So the data that I am processing, right? It's not actually continuous. I'm taking samples at certain times, right? And so that sample rate is going to give me a limit on how accurate I can be. In short, the quality of the observational measurements varies considerably from one variable to the next, right? It might be super easy to measure temperature and super hard to measure, I don't know, something like the atmospheric density at altitude, right? I don't know. That might be really difficult to measure, and you can sort of measure it and you can sort of guess at it, but it's difficult. Whereas temperature, ground temperature is fairly easy to measure. So you might have better accuracy on your ground temperature measurements than on your upper atmospheric pressure or something. I don't know. Errors in the reference data, in fact, usually are all but ignored in the evaluation of climate models. It is often argued that this is acceptable as long as these errors remain much smaller than the errors in the models themselves. So if models improve to the point where these errors are comparable to observational uncertainty, a more rigorous approach will be required. In other words, right now, I have more error coming from my models than I do from my measurements, right? In general, the measurements are more precise than the models. So, if my error bars for my model are here and my error bars for my measurement are here, this doesn't really matter, right? It's only your largest error bar that matters, because you can have this variance back and forth within this, and it won't. Like, in other words, you could have a measurement here, a measurement here, and a measurement here, and that won't tell you, right? As far as your model is concerned, these are all the same. So the only thing that matters is your largest error bar. I'm not going to go through the list of all these models because they don't really matter for us. Right. But if the models get better to the point where the models have small enough error bars that the measurement error bars really matter, then you need to change your approach, right? Right. Okay. We have an ad in progress. Hooray! I love advertisements. They are the greatest thing ever. Womp womp. Anyway, okay. In a similar vein, some of the satellite data described below are available only for a few years, whereas model climatologies are compared with such data are usually computed from 20 or more simulated years, right? the satellites have only been up for so long. And I'm probably trying to estimate what I'm trying to model what was happening before the satellites were up. Okay. For the metrics considered here, simple sampling tests performed on the model simulations indicate that the impacts of uncertainties associated with a limited observational record are small when compared to the magnitude of the current model errors. In other words, again, your primary source of error is coming from the models themselves. A full quantitative assessment of observational errors is beyond the scope of the study. We shall, however, provide for most fields some indication of the effects of observational uncertainty by comparing model simulations to two different reference data sets. So because you're comparing two different measured data sets, you can then start looking at the relative error between the two data sets. For each of the fields examined here, the reference data used are shown in table 2. Again, we're not going to... Sure. For many fields examined here, the best available reference data come from the 240-year reanalysis efforts, namely the Nkip Nkar and the ERA 40. Okay, these products blend many available measurements in a way that ensures their mutual internal consistency, as constrained by physical laws of the underlying models. While there are some important differences, blah, 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 blah. Again, we are interested in the methodology. We are not interested in the climatology that's going on here. We want to take away the model comparison methodology. That's what we really care about. So we're going to skip down here a little. And then we go over here. Beautiful. Okay. For the most part, they rely on the same observations. Although they therefore are not truly independent, these products do represent the best observational constrained estimates of the free atmosphere variables evaluated here. We shall analyze the most commonly studied levels. So these are their specific measurements. I know what TA, UA, and VA are. So these HPAs, because flipping what are they called? Atmospheric scientists are insane. They measure altitude by pressure. So these are different altitudes, right? The lower the pressure, the higher the altitude. I sort of understand why they do that. It's still a stupid way of doing it, in my humble opinion. Anyway, specific humidity plus is of fundamental importance to climate, but the accuracy of analyzed moisture is much lower than that of other state fields. Okay. Sure, so that's one of those high error fields, right? We shall use estimates of HUS from that, which include hyperspectral infrared spectrometer and an advanced microwave sounding radiometer, both carried out by the okay, blah, 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 blah. So again, these are different, right? Different metrics, and these are how they made the metrics, which is important for this paper, but not important for us. Okay, surface air fields, winds at 10 meters, and temperature and humidity at 2 meters are also obtained from reanalysis. While estimates are of reasonable quality, it is important to keep in mind that they're diagnostic both in reanalysis and climate models. Okay. They're computed from complex iterative schemes. Okay, blah, 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 blah. Thus, errors in these fields could reflect, at least in part, poor diagnostics, not fundamental model errors. Again, it's important to know where your errors are coming from. Similar caveats should be noted in comparison of mean sea level pressure, which is also diagnosed through extrapolation, both in reanalysis and climate models. In other words, even on the ground, I have a measurement here, I have a measurement here, and I extrapolate what's going on in between them. Right? I don't actually have measurements at all these places. I've measured here and here, and yeah. And these might be really, really, really far apart, especially if you're talking about oceans, right? I don't have a set of oceanic test buoys set up every 50 feet. So, okay, we compare model simulated top of the atmosphere radiation fields to data derived from the Earth radiation budget experiment. And the more recent clouds in Earth's radiant energy system. Estimates of clear sky fluxes at the top of atmosphere are less accurate than all sky fluxes, but nonetheless useful. So this is just talking about what your solar radiation is looking at, right? We are using a different stand-in for solar radiation in our data set. I'll note that, but anyway. Fine. The precipitation data, again, this is precipitation measurement, sure. Total cloud cover. The two references we've chosen for sea surface temperature, okay. Again, these are all very well and good, but we don't specifically care about them for our own purposes. Okay, these are surface heat fluxes. So in other words, how heat is moving, right? So a flux is, if I take a unit area and I look at how much is moving through that unit area, that's the flux. So you can think of it as total movement divided by total area, right? That's giving you your flux. In the following sections, these data sets will be simply referred to as observations. Cool, that's all we need. Keep in mind that observationally based or reference data is generally more appropriate. Okay. Let's get to the part we care about. Results. Monthly mean statistics. In this section, we will examine how well KIMP3 20th century simulations compared to the observations during the last 2 decades of the 20th century, 1980 to 1999. Our most complete and accurate 20-year observational record. To portray how these models perform relative to each other, we shall use simple statistical measures to quantify fidelity of their simulations. Our results will be shown in the following domains: global, tropical, and extratropical zones of the southern and northern hemisphere. Right. So in other words, they cut up their data or their models into these different sections. These regions will be respectively referred to as global, tropics, southern hemisphere, extratropical, and northern hemisphere extratropical. One statistical measure of the model fidelity is the root mean squared difference between the model simulated field and the corresponding reference field. In other words, right? When they say a reference field, let me clarify what they mean by fields here. Yeah, here a little. If I am looking at an entire area, in general, a field is defined this way, right? I have this continuous area here, and I'm going to say at some point in here, I'm going to see a force or a measurement, right? Usually, if it's a force, it's going to be a vector field. It could be a temperature field, which is a scalar field, right? But say if I have a force here, and here I have a force here, and here I have much stronger forces, right? And the closer I go to this side, the stronger my forces are, right? This could be an electrical field. This is what a force field literally is. It's saying if I were to put a test at this point, what force would it see? Right? So when they say fields, they're saying if I were to put a temperature probe at this location, what temperature would it read, right? Now, usually I'll have, a set of measurements or simulations, and then anything in between it, I'll have to extrapolate. Either I'll say there's a linear change between these or a quadratic change between these. I'll have to kind of know what the physics is that's going on. So if it's, if it's like electric field, I know that it's going to go as 1 over r squared from the distance from my the source of my field out, right? It's going to fall off quadratically. So it kind of depends what you're looking at. Okay, so they're saying there are two fields that you're setting on top of each other. Essentially, think of it like this. I have two blankets. This is going to be... Hold on with the analogy. Is going to make sense in a second, right? I have a bottom blanket that's got something under it, right? And so the blanket goes up and over, right? This is a blanket. And then above it, this is a really silly analogy, but anyway, above it, I'm holding some other blanket and I'm trying to... Hold on. And I've got some like this, right? Imagine this. I'm standing over here. I'm holding this blanket up, right? And someone else is over here. They're helping to hold this blanket up. My lovely stick figures. Right? And I'm looking at this blanket, and I had someone go and tape something under this blanket like this so that it looks like this. And now the question is, does this blanket look like this blanket? Right? In this case, this would be the reference field. So that's theoretically what's really going on. We're saying that the measurements are much closer to what's really going on. So we're going to call the measurements a reference field. And this is my simulation. Anyway, think of it like that, right? They're blankets. We're trying to guess what's underneath it. I don't know. Maybe that's off sideways, but that's the best we got right now. So, okay. For monthly mean climatological data, the most comprehensive root mean squared error statistic accounts for errors in both the spatial pattern and the annual cycle, and is calculated as follows. So I'm summing over north, south, east, west, and time, right? That's why I have the three indices there. And if I were doing the full field, right, these would be integrals, but it's actually just a sampled field. So I'm just summing over all my sample points. I'm dividing by the total number of points. I believe, yeah, W is the sum of the weight. I'm sorry. W is the sum of the weights, right? And these weights, so each point, this is the actual value at each point. You can kind of think of it, right? Or not, I'm sorry. The weights are how important each point is to the overall, right? So some points might be more important, some points might be less, or think of it like this. I am able to measure this point more accurately than that point, right? So I'm going to weight this point more than the other point, however you want to do it, right? So that weighting could just be 1, right? If this weighting is 1 for all points, then W is just the total number of I, J, K added together, right? But W doesn't have to be 1, but it can be 1, right? The easiest version of this is 1, right? And then we've got the estimated field at IJT and the measured field at IJT, right? The reference field. And then we're squaring that, dividing that by W, and that's the square of our error. So we'd have to take the square root of this to get the error, right? That's root mean squared. Easy peasy, lemmy squeezy. All right. Which for the spatial dimensions are proportional to the grid cell area, and the time are proportional to the length of each month. So in other words, these W, right? So WIJK, right? Which is, if you want, W north, south, east, west time, right? It could be that in this case. Your north, these weights are all determined by what your grid spacing is, right? What that you're using to approximate. And so you have grid spacing in distance and you have grid spacing in time as well. Right? And that's how you're determining your weights. The weights are therefore approximately proportional to the cosine of the latitude, except where there are missing data, in which case Wij equals 0. For example, over land when only ocean portion of the domain is considered. So in other words, I can use this not just to say this point is more important than that point, but I can actually use it to map out points that I care about. So if I only care about this area, I'm just going to set the weights of this area to 0, right? These weights will be 0, and these weights will be 1, or will be their appropriate weight, right? So I can use that to select out a mapping of my points. So that setup is very flexible, right? It allows you to deal with things like bias. Again, if we go back to what I was talking about with the measurement of temperature, right? If I know that this location over here, the temperature is always high by 3 degrees, every measurement, I can then, if I know that in advance, I can put that into my weights for this area. I can reduce that by 3 degrees. Right? So you can do all kinds of stuff with the weights. It's a very, very flexible system. In most cases considered here, the sums are accumulated over all 12 months and over one of the domains of interest: global, tropics, SHEX, or NEX. For these calculations, we interpolate each data set, model, and reference data as a T42 grid, which is a resolution comparable to that used in many of the models. I have no idea what a T42 grid is specifically, other than sounding like a Terminator. But apparently it's a thing. Again, for our data that we really care about, we have our own grid spacing, right? Which is going to be interesting. That's going to make things very interesting when we go to... Right, so right now, I should say this. Right now, we're looking at just a couple of spots that have data, and we're looking at data over time, right? So our spacing that we really care about is going to be the time spacing. We'll have, or we could figure out a weighting based on distance. We might be able to, so they're all like distanced from a transmitter, right? And so we could do something with this distance as a weighting. It might be a good idea, actually, if we threw in a weighting for when we start combining our model. When we start combining receiver locations for our model. Oh, yeah, right? So we have, here, hold on. We're going to have our location analysis. And then we're going to have our inter-RX analysis that will produce the distance weighting. So rather than doing a north, south, east, west, right, we're just going to do a ground distance transmitter to receiver. Oh, and then we could bring in, oh, that's genius, because then we can bring in the other transmitter that we kind of haven't really touched on, but there are technically 2 transmitters that were used for the data set that I'm looking at. One in Utah, one in Hawaii, right? Oh yeah, because then we can use that. Then we can have 3. Oh, interesting, interesting, interesting. Okay. This is something I hadn't thought of before. All right, so weighting factors when we're combining into a single thing. That's not going to be for what we need right now, but for my next trick, that's going to be very important. Cool. That's very interesting. Yeah, right. Because one of the things that I want to do, right, is, so for those who haven't been here before, I'm looking at, right, let's say I have 3 receivers and I have 2 radio transmitters. One's way the hell off in Hawaii, right? And I'm looking at ionospheric reflections at all these receivers, right? And so I have like loss amounts, right? And so right now what I can do is I can say, okay, I have X amount of loss. I have a model that I've built, right? And that model estimates I'm going to have X amount of loss, and I have essentially 3 models right now, right? And each of these models works for one of these receivers. The receivers have other biases and other things attached to them, etc., right? But what I really want to do is have a field model in the same way that they're talking about, where my ground distance becomes one of the variables of my model, right? So that I'm not restricted to these 3 locations for receivers. But in order to do that, I have to be able to estimate essentially what that weighting factor is going to be. Because if I have that weighting factor, that allows me to move around in space as well as in time, right? So I kind of already have a temporal weighting factor from all the data, all these locations. What I really need is a spatial weighting factor. And so that's part of how I'm going to be doing, and I'm also going to need a frequency weighting factor, right? Because I'm also looking at different frequencies. So my weights are going to look something like distance, time, frequency, right? Something like that. Yeah, and environment, actually. This is the big one, right? So this E is my environmental conditions. I have a whole bunch of different environmental conditions. This is actually a vector over here, right? So this, these weights are going to be based on all of these kinds of things together, and that's what the model is generating. But it's going to be important to do this in terms of weighting. That's a good way to do it. All right, cool. Thank you, paper. This is why we're going through the paper, because we can start pulling ideas across from this research area to our research area. That's the point. Okay. Brain. Anyway, we begin by making use of the Taylor diagram, which again, we went through this paper last time. The Taylor diagram, which relates on the centered root mean squared error as calculated in equation 1, but with the overall time mean, spatial mean removed. So you subtract the mean from, so you're not looking at bias essentially, right? Because you have like, here's your data, right? If here's 0, you just move this over to 0 and then you look at it, right? And that's what the Taylor diagram is looking at. The pattern correlation and the standard deviation. Okay, the pattern correlation and standard deviation, right? Those are things that we talked about. They're part of the Taylor diagram. A reference data set is plotted along the abscissa. So your quote ground truth unquote is on this point here, right at 1 on this line, and it's a polar graph, polar plot. There are pictures down. We'll take a look at them. Reference data. So okay, simulated fields are located in the first quadrant of the correlation, with the reference data. Is positive. For both the reference and any model data represented on the plot, the radial distance from the origin is proportional to the standard deviation. So in other words, this distance is telling you about the width of this set, right? Real, this is okay. The pattern correlation between the simulated field and the reference data is related to the azimuthal angle, right? So that's this. So the further angle away you are from your reference, the less correlated you are with your reference. And the centered RMS reference between the simulated field and the reference data is proportional to the distance between the 2 points, right? That distance. The observational model bias is, quote unquote, is defined as the difference between the simulated and the observed time mean. Spatial mean fields is not shown on the diagram. So again, like we said, you've already removed the bias from your reference or from your data. You're just looking at essentially the patterns. That's what the Taylor diagram tells you. It tells you about the pattern difference between two things. Thank you. Okay. Three climatological annual cycle space-time Taylor diagrams are shown in Figure 1. Hex, trop, and Nex deviations from the zonal mean. Here are some of the subsequent features. Okay, the observations are more plentiful in the northern hemisphere, which is why the results are emphasized for this region. All right, so let's take a look at Figure 1 in this paper. Let's find Figure 1. Hello, Figure 1. There's Figure 1. Okay. So these are Taylor diagrams, right? So again, this angle here, right? Let's say to right here. Let's do this a little better. Let's go to this point, right? This angle here is telling you the how correlated this is to your reference, right? And this distance here is telling you the standard deviation of yours compared to the reference, right? And then this distance here is kind of telling you, excuse me, they're sort of the ratios of them. So that's the important thing. You want to get as close as possible to this point. The closer you get to that point, the better you are. The better you match. All right. And so these are just various Taylor diagrams of the different models. Okay. How are we doing on time here? All right, we'll go for another little bit. We're not going to get through this whole paper because it's another long paper, so we'll split this into 2 streams. But yeah, so let's go until this point here. That's what we'll do. Okay. 3 climatological annual cycle space-time Taylor. Okay, we said that. Okay, in this figure, each of the colored dots represented an individual simulation made with a particular model, whereas the triangle represents the ensemble mean model. The mean model statistics are calculated after regridding each model's output to a common T42 grid and then computing the multi-model mean value at each grid cell. So in other words, you want to figure out what your variation is within the model before you start looking at how far off your model is from the measured, right? And so you run the model a bunch of times, you look at what variation happens in your model, and then you compare that to your measured, like the mean of that. Again, what they're having to do is not all of the models operate on the same grid pattern that they're using, so you have to regrid things, which means you're weighting things in different ways, right? Because you might be going from an even grid like this. Can you see that? Yeah, you can see that. you might be going to, you know, a grid that does something like this, right? Think of like a map, distortions from mapping, right? Same kind of thing, right? So in this case, this number needs to be weighted larger than this number, right? If you're going to go back to this grid, right? So it's going to change your weighting as you go back and forth. Anyway, point being, they're taking that into account. Okay. Note, because of the statistics considered here based on the sums of quadratic quantities, the error of a multi-model mean field is not the same as the mean of the error statistics of the individual models. In fact, for each variable considered in figures 1A through C, the mean model simulated field matches, in an RMS sense, the reference data more closely than most or all of the individual models. We shall return to this notable feature later. So, okay, the statistics are based on quadratics. So remember, like I said, with moving away from a, you know, like a 1 over r squared kind of field. The error of a multi-model mean field is not the same as the mean of the error statistics from the individual models. So when I put the models together, I can't just, so if I'm looking at model A and model B, and I'm saying, well, I'm going to run model A and B together, then I'm going to compare the output. I can't just slap them together and add them up, right? Okay, in figures 1A through C, so that's those Taylor diagrams down there, the mean model simulated field matches, in an RMS sense, the reference data more closely than most or all of the individual models. So what that's telling you is that some of the errors from one model are canceling out some of the errors from the other model, right? Your random fluctuations are not common amongst all models, so your random errors being damped down is what I believe is happening, but we'll see what he says later. All right. It is also clear from figures 1A through C that the accuracy of a model simulation depends on the field and domain as well as the model. Figure 1A, NHEX has some of the simulated fields have correlation with the reference data of greater than 90%, whereas other fields have much lower correlation. So again, some of your measurements are going to be better than others. And some of your simulations are going to be better, or some of the outputs of your simulations are going to be better than other outputs of your simulations, right? Now, in my case, luckily, I am just outputting one value. And that makes life a lot easier. Anyway. In addition to a range of skills across variables and models, as reflected by Center. Okay. There are large differences between different domains and between components considered. Some fields with relatively high correlations in the NHEX have lower skill in the tropics, right? So the error is going to be varying depending on how you're applying the model, right? The model might be better at some things than other things. This might be partially due to the fact that the higher latitudes, more of the variance is forced by the isolation pattern, which creates land-sea contrasts and meridional gradients that are relatively easily simulated by models, right? Things that happen in the tropics are different than things that happen in northern latitudes. That's right. And so your simulation might be better at judging what's happening in this location than that location. In figure 1C, the errors are computed on fields from which the zonal mean has been removed. And so the often dominating influence on the statistics of meridional gradients are not considered. The small scale, the smaller scale features evident in the deviations from the zonal mean are emphasized, right? So you're, again, if the thing that is you kind of your overarching cause of error is a bias error, essentially, right? You can remove that bias error. You can just literally subtract it off and just look at the other errors. This aspect of climate involving small-scale variations is often strongly affected by the internal dynamics that are more difficult to simulate accurately. So the correlations are noticeably lower, right? It's easy to subtract off 5 from all of your numbers, right? So that means that my outputs are going to be much closer when I'm talking about the error. Especially since I'm subtracting it off anyway, right? So if the majority of my error is from that extra 5 that's added to each measurement, right? I just have a bias error. Then when I remove all the bias errors, my error is going to be lower. Shocking. Anyway, note that the errors show these normalized diagrams are relative to the magnitude of the variations of the observed field as quantified by the standard deviation. So the errors have to do by the, all right, we are looking at the variations, right? We're not looking at absolute measurements. We're looking at changes. That's what he's saying. Thus, for a given apparent error shown in the diagram, the actual error will be larger for variables or domains with larger degree of variation. Wider, right? If my variation plot is wider, I have more error. Using Taylor diagrams, Pinchas et al. Et al. In 2008 discusses additional aspects of model performance, focusing on clouds, radiation, and precipitation on the CMIP3 simulations. All right, so someone else has done this, looking at a particular sub aspect of it. Okay. Okay, we've been going for an hour and 20 minutes. That's about good, I think, for this puppy right now. Because my brain starts melting out my ears. I don't know about you guys. But anyway, so this is, I think, a really good paper. This follows along neatly from our Taylor paper that this is obviously based on, or rather that this is looking to. And this is giving us inputs for our own personal research stuff. So bravo to that. Yes. Excellent. So I think we will call the end of this Sunday morning paper here. We will take it next Sunday. We'll take up our flag at this point here at starting at reference 33. And we'll keep moving forwards with this. Again, this is a very interesting paper. This is very good. This has a lot of useful information for us. Next stream. We will continue. Let's see. I might stream again either later today or tomorrow if I feel like hopping online. But the next scheduled stream will be Tuesday at what time? Let me see. I think what we're going to do is we're going to go back to Tuesday evenings. So we'll have Thursday mornings, Sunday mornings, Tuesday evenings, I think is the better way to go. So if I go try and find my last time I had a... Here we go. I'm sorry. We don't have Tuesday. I'm sorry. Our next planned stream is Wednesday evening. Right. We have The Hobbit next Wednesday. I'm sorry. My brain went back to the old thing. Okay. So I think Friday morning I have my meeting with my advisor, so I don't know if I want to do Friday mornings. Maybe we'll shift Wednesday to the mornings. What do you think? I would like to do one more morning, so I'd like to have essentially 2 mornings and 1 evening stream. So maybe we'll do Sunday, Wednesday for our morning streams and Friday for our evening stream. But not earlier. Wednesday 1 is okay for you, not earlier. Okay. So maybe early afternoon then on Wednesday. I guess we could do that. We could try that. We'll try early afternoon on Wednesday. So I will build another schedule and I will spam it out. So essentially, Monday, Tuesday, there's a high probability one or both of those days that I'll hop on for a gaming stream just for funsies, but I will not have a planned stream. Our next planned stream will be for Wednesday at 1 o'clock, 1 p.m. And then we'll keep with Friday evening for now. Yes. Yes. Okay. So that is what we will target. 1 p.m. Wednesday will be The Hobbit. We are overdue for reading The Hobbit, so we will read The Hobbit Wednesday afternoon. And figure from there. But like I said, in the meantime, there's a decent chance that today, tomorrow, Tuesday, I'll hop on stream at some point just for funsies. But we won't plan anything specific. To keep flexibility there. So, anyway, thank you everyone who was here for the Sunday morning papers. As always, I really appreciate it. I hope you enjoyed your time as we started to go through this new paper. Again, we will try and continue to move through this paper next Sunday. I think it's a very interesting paper. Connects well to what I'm doing anyway. So, at any rate, I wish you all a wonderful time. Actually, you know what? It's been a while. I'm going to go raid someone. Let's find out who's doing things. Let's see. We only have 4 people. It's fine. Whatever. Doesn't matter. Let's see what people are doing. Let's go to browse. Do we have anyone doing science and technology right now besides ourselves? Someone is installing Linux. Sure, why not? We'll go raid the person over here who's messing around with Linux. Let me famous 1 second. Hello. Yeah. 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 Hold on 1 sec. Phyllis, enjoy the raid. Sorry, I had to do the raid. Yeah. Okay. Yeah. I'll look at trying to do something different. So. Yeah. Yeah.